Right. So welcome everyone. So today I have 2 hours of lectures on close-range photogrammetry because on Thursday, if I'm not mistaken, there's a session on drone photogrammetry. We decided that I was going to give also an introduction to photogrammetry in general because I'm not quite sure how all of you are educated in that specific topic, if you have heard of it even. I know some people might not have. So I'll start with a general explanation on what photogrammetry is and what structure for motion is, because structure for motion might be a word you've heard more recently, that you might associate to some more modern ways of looking at data. So yeah, so what are these two things, and how we get data out of them. And then I have a few example cases of work in close-range photogrammetry, both in Svalbard and not in Svalbard, in cases that I think would be transferable to Svalbard study cases if that's a need. All right. So what's photogrammetry? That's the slide I usually have when I teach here at the University of Oslo, and that scares some students. But that's basically the core thing of photogrammetry. It's you take images and you do math with it. Here, what we have is basically the formula between a point in the real world, this x, y, z vector there, a point in the real world, and to the left, ij, a point in an image. So trying to find the relationship between a 3D point in the world and an image, and actually the 3D point in the world and several images. And if you think about it really, the other way around, points that you see in different images and try to find where they are in the real world. More graphic way to look at this is you have a number of images of the same scene, of the same object, depending on your context, and you want to find where is the object you're observing. So trying to get 3D geometry out of a series of images, just using rather simple projective geometry. Yes, I will start with a teeny bit of history. So in 1816, in France, the first picture is made. So that's at least the oldest one we have still a copy of. So that's a view from a window, I think somewhere in southern France, by Nice-Fourniès. Very quickly, less than 30 years later, a French military man invents photogrammetry. So his idea was, he was a bit annoyed at spending so much time in the field doing topometry using theodolites and having to get one measurement for every single point he needed to reference afterwards in his surveying work. And he was like, okay, I can use images to get a lot of points at once when I'm in the field, and then go back to the office and spend more time somewhere that's dry and warm and where I'm not going to lose anything and I'm not going to be attacked by the Germans or whatever, 1840s, maybe not. But yeah, so that was the whole idea, trying to get more data out of the same kind of field work and using this fantastic new technology that photography was. In 1867, the word photometrography appears for the first time in print. It's still not really the word photogrammetry, but we're getting there. Emil Ozda never really used any words that quite touched the sound of photogrammetry. He was using things closer to be like photography-aided surveying or something like this. Yes. So what is the workflow photogrammetry? So that's where do we get, how do we do what Emil Ozda tried to do, and of course much more modern versions of it. The workflow is rather simple. We need two sources of data. We need images taken from one camera or several cameras, depending on the case. We need georeference information. So either you have direct idea of where the camera is, if you have a GNSS system integrated to your camera, or you have points that you have photographed that you know the position of. If you have a few points, then from that you can reconstruct the position of your cameras and then reconstruct the scene. So the first thing we do is what we call the SFM bundle adjustment. So SFM, structure for motion bundle adjustment. And so that keyword, structure for motion, you might have heard before. It's really just this small step where we get the raw image data and we simply compute where the images are related to each other. So that's done automatically. You just put the images in the machine, press play, and you wait potentially a long time, and you get the position of the cameras related to each other. Not in a georeferenced space, not in a space that's even metric, but you get a mathematical relationship between the position of each camera in what I call the relative space. The next step, so the third green box from the top there, the 7-parameter transformation between this relative space and an absolute coordinate system, or whatever custom coordinate system the user wants to use, is where we get from this relative space to something that is metric, that is going to be able to be compared with other data. And for that, we need the geolocation data that's acquired at the same time as the images, or sometime not at the same time, but that's at least provided to the person doing the processing. Then we have the camera positions, and from this we can do what we call dense multi-stereo matching, or multi-stereo if we have the luxury of having more than 2 images, otherwise just stereo matching. So there we're going to reconstruct the whole 3D frame and the whole 3D scene out of the images using so image correlation. I'll talk about it later. Then we get an elevation model. From this elevation model, we can correct the images to get ortho images through the process called ortho rectification. I'll talk about it later as well. And then sometimes people want to have a point cloud of their object. It may or may not be a useful product, but in some cases it really is. And then it can be used to compare to a LiDAR point cloud, for instance, or different things. So there's different potential products being created there. The workflow I have here is more looking at something closer to a drone or plane flight, where you end up with a DM and ortho image. You could also flip this over and actually try to get a very 3D object, and then you don't really get an ortho image, you get a texture to apply to a 3D object. Yes, so let's look at this in details. What are the inputs? Inputs are images, camera information, because of course, if you just get an image, but you don't know where the camera is, you don't know how big it is, you don't know what kind of lens you have on it, it's quite hard to get the process going. So it's good to know where the camera is, or at least have a vague approximation of it. And you need location information. So either the camera knows already where it is, or you have points in your image that you can identify. Either directly, either they're going to be the targets that you place on the scene, or if you work with data that you didn't make yourself, like for instance, historical data, very old photography, or all kinds of sources, videos you grab from YouTube and extracted frames from, or something like this, then you're going to use points that you can recognize from another data source for another ortho image, from satellite data, from any other more modern or source you have a better control of, then you can get control points from. So what are images? That sounds like a very stupid question, but no question is stupid. That's an image that's somewhere in the mountains in Norway. It looks like what you would see with your eyes, but of course, from a computer perspective, that's not the way it is. From a computer perspective, it's a bunch of squares with colors in them, a few thousand pixels, they're called pixels, these squares, wide, and a few thousand pixels high. And if you look really close into the image, that's what you end up seeing. Some squares with colors, and each of these pixels have what we call an RGB value in the case of classical color images. Of course, if they're black and white images, they just have one value, it's the gray value. but yeah, so they have these three components: red, green, and blue. And here you see this kind of dark green that this pixel is. It's 73, 92, 36, which means the 92 is the largest component and it's going to be green, but there's still a bit of blue and red in there because it's not purely green. In that representation here, the maximum value would be 255, and if the three components were 255, it would be pure white, and if they all were 0, it would be pure black. Yes, so that's what an image is. That's what an image file is from the computer perspective. Once we go through all the process, we have these output products. So DEMs, so elevation models. So that's a hill-shade representation of a DEM. That's Prince Karls Forland, so this long, thin island west of Svalbard. In a DEM, you only have information about how high each point is. And if you zoom really close, so this is a color scale representation of the exact same data, but zoomed in, you realize that once again, these are just squares with a value in them. So it's also just a raster file. So you start from images, which are raster file, you do some processing, and you end up with another raster file of the same area, but this time for each square you have an elevation instead of having a color. I have on the top left there the GSD. So the GSD, the ground sampling distance, that's a very important parameter in any photogrammetry data. It's the distance between two pixels, either in the image, in the ortho image, or in the DEM. So that's how high the resolution of your product is. So a very small GSD will give you a lot of details in your image, and a very large GSD would give you a lot less details, but smaller files or files that are able to cover much larger areas. And depending on the work you want to do, of course, the GSD makes or breaks it. If you want to work on very large glaciers, you don't need to have very high resolution. If you want to work on smaller processes, on smaller glacier, if you want to look into cracks, if you want to look at permafrost processes, then you need a GSD that's going to be much smaller, and that's going to dictate, of course, what tools you're going to use. Are you going to use satellite, or are you going to go on the field with a camera? Then what's this ortho image thing? So the problem with just an image from a camera is that objects that are closer to the camera looks bigger on the image. That's just quite easy to understand. But when you then want to measure things, to compare objects, that's not a practical thing. You really need all the objects to actually be the exact same size if they are the same size in reality. So here I have a house on top of the hill and a house at the bottom of the hill. The distance makes them very highly different in size in the final image. Here's a tiny model I made for students once. On the left, it's the image out of the camera, and you see this kind of green squarey. It's a house at the top of my hill on the left, and the red one at the bottom of the hill on the right. And on the raw image, they're very vastly different in size. And the ortho image, everything is corrected, and everything is the same size. Another characteristic of ortho images is that every point in the ortho image is seen as exactly from the top, as seen vertically from the top. So you completely lose any side of objects. You only will get the top view, which is often preferable. In some cases isn't, and we'll see that with 3D objects. So that's my dad. You'll see him again in a few slides. Sometimes an ortho image of a 3D object doesn't make any sense. If you get an ortho image of my dad, you're going to see the top of his head and his shoulders. You're not going to see any of the feature of the face. You're not going to see the chin. You're not going to see the ears. You're really going to get a rather limited experience of the object. So if what you want to work on is the rock surface or something that has more than one side, that's not approximately flat like the Earth. I say the Earth is approximately flat because, well, it is on small areas. But for 3D objects, then you need a 3D model. You can't use the DM ortho image approach. In either case, you have to think quite strongly about the image acquisition method. So you could go around and just take a lot of pictures and hope it's going to work. And some people do that. But of course, being purposeful in the way images are acquired makes for, well, first, a much easier processing afterward. It makes for an optimization of the number of images you have. And overall, you end up with a better product because your images are more regularly taken, and you're going to get something that's at least more coherent. So there's two main methods. The method I call convergent, which is used to create models of very 3D objects. I call it convergent because in this case, you're going to have all the cameras pointing roughly to the same point in space. So you're going to basically go around an object, always pointing to the center or something like this. Of course, when objects get bigger or more complex in size, you don't really always look at the same place, but approximately you get something that's quite convergent. On the other hand, you have what I call the parallel method, which is used to create models of roughly planar objects. So if you're going to look at the ground, if you want to get elevation, something that's going to be comparable to a map, then you want to get to use the parallel method, where, as the name of course says, all the cameras are going to be parallel to each other. For instance, typically all looking straight down. So the convergent method, as I said, you end up with all your images that, well, it's not the first slide where it happens. I represent cameras as triangles, typically, with the sharp peak of the triangle being the camera itself, and then the lens extending as a triangle. That's a convention. It's not very important, but it comes again and again. So just so you know. So here we have an object in the middle, this red object, and pictures are taken all around it. There's a few important things to know is that if you only take 4 images or 5 images or very few images, as humans, we're still going to be able to recognize that it is the same object and recognize some features of it. Computers will really struggle. For a 360 degrees capture of an object, you're going to need to have at least 30 images. The commonly accepted distance between 2 images, it would be 10 degrees. So there would be 36 pictures to go full circle. Of course, it's very hard to visualize 10 degrees when you do it manually. So I often end up when I do this kind of survey with closer to 40, 45 images. More images rarely hurts. It hurts the processing time, but we live in a world with fast computers and with big memory cards, so that's not too much of an issue. But that's to keep in mind. If you go around your object and you only have 20 pictures on your camera, that is going to be quite a struggle to process, potentially simply impossible. But of course, a 3D object is 3D, so you also need height. So here's my dad again. And you see here I have 3 circles. I have the central circle that's taken viewing horizontally, and then I have a circle at the top that's looking down to get more details on the top of the head, and on all the features that are pointing upwards. And then I have a circle at the bottom that looks down to get below the chin, to get all the features that are pointing downwards, like also the bottom of the nose and beneath the eyelashes. Yeah, so a convergent method is not only a 2D thing, it's really, you need a 3D approach. And of course, the more complex the object, the more you're going to have to think about, do I have more than one image seeing each feature of my object? So if you have something that's really a complex concave object, then you're going to have to start thinking about the trajectory of your camera when you go around the object of interest. Sometimes you might actually need to do some more vertical arcs, like starting in front and going over the objects on top of just these horizontal circles. Yeah. So how do you plan this kind of survey? As always, you need to think, what is the resolution that makes sense for me? So what is my ground sample distance? In the case of a 3D object, it's a bit less well defined than in the case of a flight. But basically, how much information do you need? Like, do you want to see every single crevasse in your rock? Do you just want to see the general shape? You really need to think about what you need. If you're gonna need a very, very high precision model of things, then sometimes just doing a circle around the object is not gonna give you enough resolution. Then you're gonna have to actually do a lot of circles looking closer to the object, and you're not gonna see the whole object in every image, and then the number of images suddenly completely explodes and it gets way more complex. But of course, always that's the first question. I want to do photogrammetry acquisition. I want to get the 3D model of an object. What resolution do I need? How close do I need to get to the object? Then the next three parameters here, the size of a pixel, so the physical size of a photoreceptor on the camera. That's something you have to think about, or at least be conscious about. And the size of your sensor, this is like size X and size Y. So from these two information, you get to know how big your sensor is, and then you have your focal length, which is the optical element in front of your camera. And from that, you get to compute the scale. So the formula on the right there, the ground sampling distance is h, the distance to the object, h because usually it's the heights when you fly. So keep the h as the distance, multiplied by the size of the pixel divided by your focal length. That gives you the resolution, the ground sampling distance at the image level. And then, of course, what I was talking about with my circle, the overlap between two images is here expressed in terms of angles between line of sight. So typically, I say between 5 and 15. If you get 15 degrees, it's already really on the large end, and I would really advise to get closer to 5, between 5 and 10. Yes. Second method, the parallel method. So here we have a bunch of cameras that look straight down to the scene. There's no angles to think about. You just want your cameras to be as vertical as possible. When you are with a plane or with a drone or this kind of things, the verticality is kind of taken care of for you. If you're going to do a survey by hand, if you're going to go into field and take images, then you're going to have to think about it and make sure that you can have your cameras pointing as vertically as possible. The problem with images not looking straight down is that the GSD is actually not consistent in the whole image. If you have a very oblique image, so oblique is, so nadir would be pointing down and oblique would be not pointing down. The points that are closer to the image, closer to the camera, are going to have a much higher GSD than the points that are much further away. Sometimes you even see the horizon, and of course the horizon is an infinitely large ground sampling distance. For these images, it's much harder to recognize the same objects from an image to the next because the scales are going to be vastly different, and keeping consistent scales between images is necessary to be able to recognize objects. That's an example of a survey. So that's up northwest of Njølesund on some sorted circles. I'll actually come back to that case later, and that's actually the data we're going to have a look into this afternoon. So here you see a number of lines of flight taken parallel to each other, looking at the central object. You might also see that the lines are not quite regularly spaced. That's because the object of interest is in the middle of the scene, and I don't want to step on it. So there's a bit of leeway there. The image is not perfectly vertical, but that's what's attempted. It's to get a grid of images in lines. So here, how do you compute your parameters, and how are you gonna so fly if you have a plane or a drone, or hold your camera if you're doing it manually? You always have to consider the same kind of parameters. What's your focal? What's your camera? So the size of your sensor, and then how high you want to be. That gives you your GSD, and then compute this B parameter, called the base, which helps you decide the overlap. So the overlap is the amount of the percentage of your scene that is going to be seen from image number 1 and then going to be seen again in image number 2. To do any kind of stereo reconstruction, you need to see any point of the ground at least twice. I say at least twice because as a general rule of statistics, the more observations you have of the same objects, the higher quality you will get a measurement of it. So here we talk of overlap. The theoretical minimum is 50%, but of course you can't be sure you have 50% unless the world is absolutely flat and the terrain is completely uninteresting. The second you start having some terrain, if you compute your overlap to be 50%, you're actually going to have some holes. So even in traditional photogrammetry, where we're using film and everything was very costly, the overlap is always at least 60%. So you have a 10% margin of error to account for terrain, to account for just actual operator error when you take pictures. If you're a bit too slow, you walked a bit too far between two pictures. So that's very important to say, at least 60%. In the modern world, where we have an unlimited amount of storage on our cameras, we always take at least 80%, which actually ensures that we have more than 2 images. We have at least 2, so 2, 3, 4 images sometimes of the same points, even in a single line of acquisition. So that's adding more strength to the modeling. So that's the overlap. Of course, it's not a single line of flight you're doing. Usually an object is a bit larger. And actually, even if your object could be photographed in a single line, it's a good habit to make more than one line, because that really adds some strength to the constraints of the geometry. A single line of images, the math can actually diverge a bit and end up being relatively soft. So if you have 2 lines of images, then you suddenly add a second dimension to the constraints of the images related to each other. So then you have to think about 2 types of overlap that were called the long track overlap. So the overlap between 2 images taken one after the other, and the cross-track overlap, which is the overlap between 2 different lines of images covering the same objects. It's not as crucial to have a very high cross-track overlap between 2 bands of images as it is to have a very high overlap between images in the same band. But a strong overlap in the cross-track, first, it adds another observation of the same points, and that's never bad. And 2, the larger the overlap, the tighter the 2 bands are going to be attached together. If you have here in this figure, the overlap is probably something like 20%. That's enough to tie things together, but that's not necessarily enough to give a very high level of confidence in how the 2 things are together. You can basically imagine each image as a sheet of paper, and the overlap being where you put glue between images. If you have only glue on a tiny sliver between 2 images, it's relatively light, it might break. It might happen that in that overlap is an area of the ground where there's not much features, nothing really to see, and so your glue just doesn't stick. The larger amounts of overlap you have, the larger amount of glue you have between your images. So that's what's important. Of course, there's the return on investment is not always so great. Having 95% overlap is just taking too many pictures. So the usual recommendation I have and I give to students and to people I work with is to take 80% overlap along track and about 60% overlap across track. So 60% overlap across track gives you full stereo between the two lines of flight, and that really helps. In some cases, when you have when you work on a city, for instance, or anything that has like very sharp edged buildings or structures or things with vertical walls, then you kind of want to have a lot of images, because part of the ground is going to be obstructed by the structures on it. So there the recommendation goes higher and higher, but that's very case specific. The general recommendation: 80% overlap inside of a band and 20% and 60% overlap, across bands. These are the formulas. There's not really any point to go very deep in details here. It's a bit the same as for a convergent acquisition. You want to think about your ground sampling distance, and that's the same formula as before. Here, the height is really the distance vertically, except of course you can flip that whole system 90 degrees. And if you're interested in taking a survey of a cliff, for instance, or the wall of a building, if you work in urban context, then h becomes the distance between the camera and the wall or the cliff or the vertical structure. And then it's not height anymore. It's just the distance. And then at the bottom there, I have the formulas to quickly compute what's your overlap. Very often, you want the formula to be flipped, because the overlap is something that you decide on. Say, I want 80%, and then you have to compute these B and D distance. B is the distance between two images, and D the distance between two bands of images. So, well, but that's easy enough to flip this kind of formula. So there you have your survey planning. That's quite crucial. That's really something you need to think about before you go to the field, because it might actually be the one thing that's going to help you choose what equipment to bring. If you have a camera, the only camera you have available has a very specific lens, and you can't change it, then you're going to have to increase or decrease the distance between you and the object. And if the distance you're going to have to need with the object is 1 meter, that's usually not a problem, because you can hold the camera 1 meter over the ground, or you can be 1 meter away from the object of interest. If the distance really increases, you can't hold the camera 3 meters over the object just with your hand. You're going to need to have additional equipment for this, or you're going to need to actually take a drone, because your camera is just not going to work. So when you start to say, okay, I'm interested in this object, very quickly you get to say, okay, then what is the appropriate camera? Do I need to buy another camera? Do I need to buy another lens for my camera? Do I actually need to get into the air? Is my survey approach not going to be possible given the parameters I need for the science? And then there's another thing that's incredibly important and very often overlooked by newcomers to the field, is reference points, ground control points. More and more cameras or drones or systems have a GPS integrated to them, but very often they're not great. If you work with a consumer grade drone, for instance, the kind of things you can buy for, $1,000, a few thousand euros, dollars, pounds, whatever unit you want to use, these things come with a GPS in them, but it's a very bad GPS. It can be wrong by tens of meters in the Z dimension, particularly. So it's a kind of data that can be helpful, but that's not going to be helpful enough to get a well georeference model. And you want to have well georeference model and well scale model, because that's where your science happens. If you have a model that might actually not be geometrically well constrained, where the scale might not be right, then the math you're going to apply to it, the models you're going to use on it, the comparison with a model either of the same area taken at a different time or of a different area that is somehow comparable, it's not going to work, because you need to have a good, well-constrained idea of the exact geometry of your area. So you need ground control points. So here in this figure, I have very glaring colors. In red is the area of interest. That's what you really want to have. So that's your mountain peak, that's your sorted circle, that's your permafrost structure, that's whatever you want. That's what you want to have data on. The first thing you have is these cyan light blue points. These are the 5 points that you want to have that are not negotiable. Mathematically, 3 points can be enough to get the math to work. But if you only have 3 points, then you're not going to encompass your whole area very well. And any points of your area of interest that's outside of the polygon that's defined by your control points, it's not controlled. It might completely diverge, as any model does. So you need constraints. Here I have 4 corners to like define the area where I know where I am, and then I have this point in the middle to anchor the model. Because the same way as you have glue between images to get them well together, you also need nails on the ground to put the overall sheets in the coordinate system. It's the same analogy. Once you have glued all your pieces of paper together, if you want to attach them to the wall, you can put the 4 corners and it can be kind of tight, but it might still be a bit floating, and maybe actually the glue might not hold so well, and you might end up having your sheets kind of getting a bit too far away from each other in the middle because they're not well constrained. So you need to have reference points, not only the minimum, not only 3, not only just covering the edge, but also in the inside. The purple points, there are more points. The more points you can have, the better it is. Because then you can use these points to better constrain your models, to make sure that smaller areas are better constrained themselves. And if you really are able to get a lot of points, you can also decide to use only half of the points in the processing, and then keep half of the points to be independent controls at the end. And that's what's in a very professional processing surveying context, that's what's always done. There's a lot of points that are just kept out of the processing, and once the model is finished, the points are controlled and say, okay, how far are we between the model that did not use this point as a constraint and that point as a ground truth? So that you end up having a real way to estimate the quality of a model, because that's a question that always comes up. Oh, I done a model, what's the quality of it? If you don't have a ground truth that's independent from the image processing, it's basically impossible to say. There's sometimes you can use the quality of the correlation of the images. There's some hints that can tell you a few things, but as a general rule, you don't know. It's the only way to have a real control is an external source of data that wasn't used in the processing. So more GCPs, more better is my mantra on this. Of course, getting GCPs is not always particularly easy. You can get them with a GNSS survey. So there you come with the traditional RTK GNSS antenna or these kind of things. And then you're going to get a number of points. With RTK, you can actually get quite a few. Of course, you need to capture points that you're going to be able to identify on your images afterwards. And there, the problem of identification can actually be rather large. You need to be able to see the points in your images, so they need to be either marked or they need to be very clear natural objects. and they need to be also about a comparable size to your ground sampling distance. So if you find a big white rock in the middle of some darker rocks or sand or something, and you measure it, if the rock is 50 centimeters wide and your GSD is 1 centimeter, it's not going to help you very much because it's going to be quite blurry. If your GSD is really small, the GPS is not going to be precise enough, because even the most careful GNSS survey, not in RTK, but like taking long stations, like getting minutes and minutes and hours even of observation of a single point, you're not going to get very, very accurate. You might get to the centimeter range. With RTK, you're closer to 3 to 5 usually. So if your survey needs to be more accurate than this, and that happens when you have a very small area you work on and you want very high resolution, then GPS is not going to be good enough. Especially if you want to compare year to year, some very slow, very small processes, the GPS is not going to be able to give you a good absolute reference. So if you need to get more accurate, you end up using more classical topographic methods with a total station, a theodolite, to measure a number of points related to each other. So here, the accuracy can get much better than a millimeter. You can really get very high precision points. But of course, then they're not linked to the global reference system. But of course, do you really need to know exactly where on the Earth you are to the millimeter when you're working on the movement of a small permafrost process? My answer is no, you do not need that. You just need to know where you are in your very local frame. So if you're going to have to do repeat survey at the same place, my advice is to try to find an object that's not going to move, or a few objects that are not going to move, mark them to get stable reference points, and then you can get points that you're going to remeasure every time you go that are on the ground, potentially moving, but that's okay, because for one survey, you're going to have a stable ground, and then when you come back, you can use the stable frame again, and just have this mini world that's not projected in UGM or in whatever other coordinate system, but is a local frame. The last method that I've used a few times is using an object that is going to be your reference frame. For instance, a very high quality, high precision, just square, like 4 pieces of wood or metal attached together with some points on it that are accurately measured one way or another. And then you could use this to just put it on the object of interest, put it around the object of interest, you take your images, and then you have this frame, this object of very well-known size with points that you have a good idea of the position in absolute, as an absolute frame of reference. So then you end up similarly as if you had a theodolite and did a survey, but much faster and without having to actually carry the, well, things to put in the ground, like for paint or identifiers. You don't have to carry that, and you don't need to carry a heavy theodolite, which is, of course, a expensive, fragile piece of equipment, whereas a well-designed frame to just drop on the ground and take pictures of is a very cheap option. So that's my last advice here. Yes, so that's the workflow again. So now we have images, we have GCPs. What's my next slide? Yep, yeah. Okay, then we need, so now we have the input data. We plan our survey, we know how to take the images, we know how to acquire our georeference information. We can put everything in the machine. So the first step is we need to find type points. So as what's on the left there is telling you, this is now done automatically. There's a method that came out in 2004 called SIFT. That's so scale invariant feature transform. That's how it's called. And that's an automatic way to detecting points that are the same in a bunch of images. There's more modern versions of this, something called SURF, and there's ASIFT, and there's a whole collection of similar algorithms. I'm not going to get into it, but that's automatic. Historically, type points, of course, you had to find them manually. So you would take two images and you would try to find points that you could recognize between two images in these positions. You notice that the numbers are a bit weirdly placed. For that, you have to blame Mr. von Gruber, who came up with the idea, I think, over 100 years ago. They're in this order because that's a simple way to find things. You're gonna have an easier time finding a point in the center of the image, and from this, it's easier to like put the images together. To finding 1, 2, 3, 4, 5, 6 in this order is pretty good. Then that only gives you 6 points of reference between two images, which may or may not be enough, especially if your images are not great in terms of optical quality of the camera or things like this. So what we do with it there, that's an example here. That's two images over the volcano in Jan Mayen, and each of these square represent an area where you're going to look for a type point, and then you're going to select a rock there. You're going to select some snow features or whatever. It doesn't really matter. You're going to be able to identify things to put the images together. SIFT, the automatic algorithm, is going to find a lot of points. So here, every single red point on the two images, so that's over a field somewhere close to Oslo, taken with a drone, but all of these points, they're points that have been identified as pairs between the top image and the bottom image. Of course, you see that the overlap area there. So whatever is at the very bottom of the bottom image or the top of the top image, they're not overlapped between the two images. So of course, there's no type points to be found there. And you might also see that they're not well spread. In that case, they're only visible in the grass because the grass has a lot of structure, there's a lot of texture, there are a lot of things that look quite unique. The tarmac there, the driveway or whatever you want to call this, it's a very uniform gray area, and there the computer is not able to actually identify points reasonably, saying, okay, these are points that are the same. It just looks gray and homogeneous to the computer, and so it gets completely blank. That can be an issue because, of course, it means that you don't have the glue there between the two images. But if you have enough points, that should be enough. At the top there, I have a box that says obvious outliers. These are points that are not in the area where there's an overlap. So these are obviously wrong. They can't possibly be real matches. These happen, but of course there you can count them. There's 8 or something. If there's 8 points that are wrong and 2,000 points that are right, it's fine. You can just carry on with your life and just use these points. And then the math is gonna either remove them from the computation automatically, or they're just going to be modeled in the rest. Less easy to see, there's actually quite a few other points that are wrong. Not quite sure I can pinpoint one right now, but there's going to be some other points that are wrong because things look similar. What looks more like grass than another piece of grass, I don't know. So there's going to be a few errors, but the overall amount of points is going to be enough to ignore the errors and the outliers and keep on working. So that's done completely automatically between either every single possible pair of images or guided by the user or by some additional data. You might only want to try to find points between images that you know have points in common to make the process quite a bit faster. And then once you have these points, you can do what we call the calibration and the orientation. So that's actually finding the parameters for this big formula I had in my first slide. L being an object and K being an image. You're trying to find the position of that object in the image or the position of the point in the image in the real world, either way. And for that, you're going to need to find where your camera is. So that's this C, the center, the optical center of the camera. You have to find which direction the camera is pointing. Is it pointing up, down, to the side, any possible angle? So that's R, that's the rotation matrix there. Then you're going to have to get from these 3D points into a 2D frame, because an image is only a 2D thing. So use this pi as the projection function. And then this weird letter that I'm not exactly sure how it's called, to the left of the formula, that's the camera parameter. So once you know where your camera is, where it's pointing, and you got into a 2D frame, then you need to say, okay, but my focal only looks this wide or this short, and the camera has distortion. Is it a fisheye? Is it all kind of parameters of the camera? They all encompass into this this single function. So that's really getting from a perfect projected point into what the camera actually really is physically. So that part is the calibration and finding the matrix, the rotation matrix R, and the center, the optical center C. That's what we call the orientation. You might also encounter internal and external orientation as words to describe this. So the internal orientation is the calibration of the camera, and the external orientation is its position and rotation. So how do we use this to get? So how do we use the type points to get into the orientation? That's a small figure should give you a bit of a, at least an understanding of it, if not the math, because well, that's not quite relevant for us right now. But the idea is that if the cameras see the same object and are able to identify, so in this case I have identified the corners, then we're going to be able to compute the intersection and get the math together. It's somewhat complex, but it's, from a user perspective, completely abstracted, of course. We're going to be able to find where each camera is with each other just with these few points. The same way as you need, in theory, only 3 points, 3 GCPs to get from a relative space without the metric, without anything, into a space that does have a metric and does have an orientation and does have, you know, a north and everything. Is the same here. You just need very few points between two images. If you know the 3D position of a point, that's a good start. If you don't know, you just know the 2D position in several images, that also works. You just need a few more points. But of course, using the SIFT method or whatever automatic type point detection, you have thousands of points, and you just need to find a few parameters for each image. So typically, so 7. So once you have this relative position of things, you do the absolute orientation. So you need to register georeference. That's a different way of saying of describing this. So register this model into an absolute frame of reference, either a global thing, UTM or something, or your local coordinate system. It's a process that's, I'd say, almost always needed. The cases where you don't need it are kind of very similar. If you think about 20 slides ago with my dad's face, I wasn't very interested in knowing the metrics of his face. I wanted just to have a model, and then I could do things with it, so put it in video games or whatever. Then I don't need to have a metric because I can just scale it afterwards, and being absolutely accurate is not relevant. But the second you start to think about science, and I think most of us here are thinking about science, scaling is important. Is this rock 1 meter wide or 5 meters wide or 2 millimeter wide? It's really going to influence quite a lot whatever analysis you're going to have on your final product. So you're going to need at least the scale. So as I said, you need at least 3 points to do the absolute orientation. I say 3 non-collinear points because, of course, if you have 3 points that are on the same line, then you're going to still have one free parameter, and the whole model could rotate around this line that's forming the 3 points. You need 3 points are not collinear, and of course, you need to see these points in at least 2 images, because if you just see the point in one image, then you don't have the ability to know its 3D position. If you don't know its 3D position in the relative space, on top of knowing the 3D position in the absolute space, then you can't compute the transformation. So you need to see these 3 points that are not collinear to each other, and you need to see them in at least 2 images. Of course, as always, if you see them in more images, it's better. If you have more than 3 points, it's better. The more points, the happier your math is going to be. And from that, you estimate 7 parameters between your relative space and the absolute space, the 3 rotations, so in each axis, 3 translations on each axis, and a scale factor. The formula looks like this. You might realize that it's quite similar actually to the formula I had before. You just don't have the projection into a 2D space. There we stay in a 3D space. Back to my workflow. So now we have the 7 parameter transformation done, and we get to this absolute camera position. From that, we can actually finally try to get into a 3D model. If you've used, actually, I think any photogrammetry software before, you might remember that before you do this dense stereo matching step, you already have some kind of point cloud. That's because once you know the absolute camera position or even the relative camera position, as a byproduct, you also know the position of all of your type points, and you can extract a 3D representation of the position of all these type points. That's not going to be a model. The distribution of these points is going to be, well, as you saw for the car park example, you're only going to have points on the grass and none on the car park itself. So that's a very imperfect product, but that's a nice way to visualize, and we'll talk about it this afternoon in the hands-on. But yes, so when you get to that point, you don't actually have a full model of the object of interest. So you need to do what we call dense multi-stereo matching, or as I said before, only stereo matching if you don't have the luxury of 3 images or more than 2 images. Stereo matching. So what's the idea is that you have the position of your cameras there in orange, camera 1 and camera 2, and you have this statue there, and you need to find which points are representing the same object for every point of your scene. So the SIFs will tell you a few points. In the correlation, you're going to be like, okay, I want for every single point of my object, I want to attempt to find an homologous point in other images to find a 3D position. This is the ugly bad formula of a correlation score. That's basically just a way to say, okay, this part of an image compared to this part of another image, do they look the same? And that's going to give you a score between 0 and 1, or between -1 and 1, actually. 1 being, oh, that's exactly the same thing. I absolutely recognized it. 0 being, there's no resemblance. And -1 being, oh, that's actually the exact invert of the image. That's not often relevant. The reason we use a correlation score and not like we're not ever actually looking for 1 as the correlation score is because from 2 images, they're never going to be taken from the exact same point of view. And so the same object in the real world, they're going to be a tiny bit different between 2 images because the view angle is going to be a tiny bit different. So there you can have a slight misalignment, and the correlation score is going to fall below 1. Usually still probably more than 0.7, 0.8, depending on your scene, depending on the angle differences, of course. Here as an example, before we go for a break, that's that same image of this statue. In the top middle there, I have a snippet taken from, so that's the right eye of the, well, the left eye of the statue, but the eye we see on the right from our perspective. And on the right, I have the correlation score. And you see that, of course, at the right position, so where the left eye on the right there, you reach 1, because there it's actually taken from the exact same image. And so there's one point in the image where, yes, this is exactly right. But you also see that there's a lot of other parts of the image where it gets also quite high. Typically here, the other eye of the statue, it has a similar structure with the bright center and then the dark around the eye and then bright again outside of it. And so you end up having some points that are rather similar, even if they're not the same. And even there, the whole left part of the image on the, like on the hair, somehow it has a similar general structure. So here we really see that we have a problem. If we just compare two images and for each point in each image, try to find the homologous point in another image, knowing that we're not going to find the one-to-one relation because they don't have the exact same perspective, you might end up in a situation where the correlation actually is better at another point than the point where the correlation should be, where the homologous point really is. And now it's 10 o'clock. I'm going to let everybody have a break and find myself a coffee or whatever. And we'll see the rest. So there's a few more slides on the theory, and then we get to the fun science examples. Yes.
Thank you, Luke. And do you have any quick questions before we go for a break, or we can take questions later after the second talk?
If there's questions, I'm happy to take them.
Yes. Any quick question to Luke?
I may ask one question.
Yes.
Yep.
Thanks for the great talk, Luke, first of all. And I'd like to ask regarding one of the initial slides, definitely the first half of your lecture. You
Yep.
were referring to the ground control points.
Yep.
And you see, yeah, this one, and the one central reference point should have this XYZ coordinates, and while the other supplementary ones, which are like magenta, I guess, colored, they should have XY and or Z. So in this case, you're saying we can, for example, take X and Y coordinates without the elevation when we're talking about the supporting points.
Yeah. So of course, it's always better to have X, Y, and Z because then you have the full package. But in some cases, you might. It's mostly in cases where you're going to be limited to the way to get points. And for instance, you're going to have to use maps where you don't have good elevation on them or something to still try to find something, and then you only have an XY. So these are points that are going to still be helpful because they're going to give a constraint to your model in at least some respects in 1 or 2 dimensions. And so that's better than nothing, but that's really just in some edge cases where that ends up being a helpful thing to have only some elevation. And it can be, for instance, you have images and then you see it on the images, you have a marker that was put there by someone else at some other point, and that just tell you, okay, this point is at 1200 meters of elevation, but you don't know the X and Y. So you can use that as a control or as an additional constraint if somehow you don't have enough constraints. But the general rule is the more XYZ points you can have, the better, and the rest are really just helpers.
Thank you. Understand.
Yeah. All right, let's go. Okay, so I left you half an hour ago with this and a very quick introduction to what image correlation is. So the idea is to be able to score the likeliness of two different patch of two different images. But of course, as I was saying, there's a problem that you're never going to get one score because things are a bit different. And in many contexts, you're going to have a lot of things that look like each other. And so you need to have a way to not try to correlate every point of every image into every other point of every other image. And by the way, that would take an insane amount of time, and it would be very computing intensive. And that's also something we want to avoid. So in order to limit the amount of points that we're going to try to find correlation scores on, we use what we call epipolar lines. So the idea is that you take, so in the convergent method, it's going to be a bit similar with a parallel method, but in the convergent method, you take one image as your master image, and for each point, you're going to draw a line out into the world using the formula I had in my first slide. The idea is that you're able to project one point into a line in the outside world. Then on that line, you're going to take a sample of points and project them into the secondary image. And from that, you're going to create a line. That line is most likely not going to be straight because it's going to be subject to distortion, and the perspective is going to be a bit different, and a number of things. But you end up with a series of points to try to find correlation scores on. And there, instead of looking in the whole 2D space of the secondary image, you only look for a few points. So in that specific case, if we're looking for the eye, which is not what my figure shows apparently, but if we were looking for the eye, we would not try to look at the wrong eye. So this other high spot of correlation, the correlation is very high. We're not going to attempt to find the score there, and so we're not going to risk being mistaken with this. So this is basically a way to drastically limit the computing time and also the chance of getting wrong information. There's also one other thing that actually I can talk about here, is the size of the snippet you're going to try to look at is highly relevant. So in that case, I was trying to find this rather large patch of image with the whole eye, and that gives a lot of information, and it makes the patch quite unique. And so you're going to be able to find with a relatively high confidence the point in the other image. But of course, trying to correlate with large patches of images is relatively slow, and it's not very precise, because if you're 1 or 2 pixels off, it's still going to look quite similar. And because you're not going to find the exact point, as you've been saying. Sorry? No. Yeah, so you're not going to be able to find the exact point. And so the size of the window and the amount of information might actually give you a bit of floating. So you could get a much smaller patch to try to find. But of course, the smaller the patch, the more generic it's going to look. So if you get a patch that's just like 3 by 3 pixels, it's basically just a few shades of gray, and it looks like everything else. So there's kind of a balance to find between how small the patch is, which makes the computation more efficient, and the scoring and the finding more precise, but also it makes the point less unique. There's a way to combine these two things. I will talk about it a tiny bit later. So in the case of the parallel method, we don't really have an image that's going to see a large amount of part of the scene. And so what we do is we completely flip the problem over, and we actually try to look for each point in XY of the scene for a grid that we predefine before starting the correlation. We're going to try to find the elevation at which we find the same patch in all the images that see this. So in that small example here, we have this vertical line with the red dots, which is one coordinate in XY in the world. And we're going to try to find at each of the elevation represented by the red dots, what does the image look like? And we're going to realize that at the point of the elevation that actually corresponds with the terrain, we're going to find points that look similar enough. And then we're going to register that as the elevation for that XY coordinates. And then we're going to move to the next one. But of course, so as I was saying, if you take a small patch, it looks very generic and it's going to look the same all the time. And so what we do to make it faster and also avoid getting false matches and then a lot of noise, of course, is we do what we call multi-scale matching. So instead of trying to find for each point of the image at full resolution the right elevation or the right distance, we're actually going to first do the process at very low resolution. And there's not very many different places to check. And even a relatively small patch of image, like 3 by 3 pixel, because we had such a low resolution, it's actually a rather large part of the image. And then from this, we're going to be able to find a rough idea of the geometry. And then from that, we're going to be able to constrain. Instead of just on the whole line projected, we're going to be able to try to look for a match on a smaller segment. And then once again, avoid looking for places where correlation might actually be higher, but wrong. So in this example, we start at the top left with a very low resolution. We only end up with 4 different distance or elevation if it was a DEM. And then we go to a higher resolution. So we see that the front of the face, where the nose is relatively close. The chest is protruding, so it's even closer. And then the back of the head and the hair is black, that represents further away. And then at the second step, this gets refined a tiny bit. So we have twice as much resolution, so it's 4 times more points. And we start to have a bit more details. We see that the nose and the chin are actually protruding, but not so much around the eyes. And then the further we go, the more and more resolution we have, the more and more details we have. And we keep a model that's rather clean. We don't have much noise. We don't have blunders or large errors, because we have constrained the matching, and we have constrained the algorithm to only look for correlation in the area where we know we want to find it. The example for looking for terrain looks like this. That's the initial step. We have the world, my terrain there in this rocky texture, and the initial space that we try to find elevation is, from 0 to a given elevation. In some software, you can actually set that up, that you want to look for a range of elevation to find your elevation in the terrain, but basically try to find on a very large area. And we're going to find these green dots at low resolution there every 4 squares. From this, we're going to define an elevation model that's quite rough. So there, this red band, and we're going to say, okay, we're going to get points at higher resolution in more points, but we're only going to look in this red band to try to find points, which gives us this. So the red points there, they were all in the red band. And it allowed us to find them much faster, because we didn't try to look into the green space. We only look into the red space. And then from these red dots, we say, okay, we have points at a slightly higher resolution again. Then we can estimate a higher resolution DEM and a thinner band to try to find points at even higher resolution. And we get to this blue line with the blue dots that represents the terrain rather well. And at some point we have to say, okay, we're good enough, we have a high enough resolution, and we just stop. So we can always go one more step, one more step, one more step, until the images don't warrant going further. But basically, it's rather easy to just add more steps and look thinner and thinner and thinner, and have a tighter and tighter look. So that would be the final DEM there if we stopped at the blue step. As you can see, for most of the terrain, it fits quite well. On the right there, there's a peak that's not captured because, well, it actually doesn't quite follow the grid that we have, and so it's going to be ignored. So that's going to be something that's always going to happen with this kind of data, a DEM only going to be able to capture features that are about the size of its GSD, or actually bigger than its GSD, because yeah, you only have a certain sampling of the world, and so if you have a peak that is just between two sample points, it's going to be smoothed out. So that's why you might want to get higher and higher resolution depending on what you want to do. But that's what the DEM is going to look like. Yes. So once you have this elevation model in 3 dimensions at the resolution you want, very often you would want to have an image to superimpose to this, so either a texture or an image. For that, you need to correct the images through auto-rectification. The auto-rectification process is actually very simple. You have your grid of points that are at the resolution of the DEM, or even at any other resolution that you might want. You might actually, quite often you get an ortho image that's going to be higher resolution than the DEM, because you're looking at the details in the image from a human perspective is sometimes more important than just the pure geometry, and sometimes that's actually the only thing of interest is the image and not the elevation. And there, so the process is quite simple. You take for each point of your grid, in the same way as for each point of the grid, you look for an elevation. There, for each point of your grid, you're going to look for a color. So how do you do that? You take your point. Each point has an XY coordinate that comes from just what it is. You're going to use the DEM to find the Z value there, eventually interpolate it if you're not exactly on a point where the DEM has a value, so some kind of bilinear interpolation or whatever you like. So you find the third dimension. Then using the big formula I had in my first slide, you can project that point into the image space. And from the image space, you can grab the RGB value, or if it's a black and white image, the gray value, the color of that point. And then you take that color and you put it in your grid. And then you move to the next one and you do the same process over and over again. By doing this thing, you are going to find a regular grid of color, and you are going to have a perfect sampling that's going to be exactly at your ground sampling distance. That works for if you have to correct one image. Of course, then you need to do a mosaic of all of these images. I don't have a slide about that, but the idea is once you have all of your corrected images, you're going to try to put them together, merge them together. There's more or less complex ways of doing this. Trying to find lines where the distinction between two images is going to be the least visible. So that's more of an aesthetic approach, or trying to correct for color variation between an image to another. So there's a lot of technique, but basically it's just taking all these tiles that are themselves ortho images and do what we call an ortho mosaic, so a bunch of images. Before I move to examples of close range photogrammetry, just a few words on what is a good image. That's a question that comes rather often, is my camera good enough? What's the problem with my image? And things like this. A good image is an image that doesn't have much noise. So here at the bottom, I show two images. They're actually the same one, but one of them has a lot of noise. So if you look at it, it has this like weird grainy thing and colors that don't make any sense. There's some green and purples in the sky instead of being homogeneous blue. It doesn't look super good. And from a computer perspective, all of these color changes and noise and grain, that's going to be identified as a structure, as something that is data, that has value. And if you have these kind of things, then you're going to be completely unable to recognize the same object from an image from another, because the noise is random. It's not related to what actually is in the world and what object you actually try to recognize. It's an additional layer of data that models your ability to recognize anything. So you really want to get images that are the least noisy possible. So in your camera, it means putting the ISO value low. It also means usually the bigger camera, the more fancy ones tend to take images with lower noise. Noise is something that you're going to see a lot in images you take from phones. Except that, of course, phones have some post-processing things and they try to mask the noise. But every time there's some post-processing applied to images, you actually lose a bit of the reality. And you end up with something that's blurry and or with reconstructed contrasts that are not quite real. So a good camera that can take good images that don't have noise and that does not do any post-processing automatically that's going to affect the realness of the image is what you want to have. Then I say you don't want any burnt areas, so areas that are completely white or completely black, because of course, if the image is just a bunch of completely black pixels or completely white pixels, there's no data there. It's like if you scream into your microphone, it's just a bunch of noise. There's nothing more to be recorded. You lose definition, you lose details, up to nothing. And if you use completely white areas, completely black areas, that's going to be areas of your images where you're not going to be able to reconstruct anything. It's a lost spot. And then the last thing is you want to have the highest contrast possible. Because if you take an image and everything looks a bit gray, then you have very low color resolution and then everything looks a bit the same. And you're going to lose also a lot of contrast, a lot of textures, and you're going to end up with a model that either is going to fail in some areas or is going to be rather soft and undefined. So you want images that look strong, look quite punchy, but without going too much contrast where they suddenly actually lose complete information in the shadows or in the brighter areas. So taking good images, that's closer to the world of photography than the world of photogrammetry, but that's something that you have to think about when you're taking images and choosing your equipment. And then there's bad objects. So photogrammetry works great on a lot of objects, but sometimes it just doesn't. This example there, it's a reflective object. So the problem with the reflective object is that if you take a picture of it, you're not really seeing the object, you're seeing whatever else is in the room or whatever else is in the world, you're going to see something else. So you're not going to be able to reconstruct anything because the second you move your camera, what the object is reflecting is going to be different. So that's a complete no-go. So you can't work with reflective objects. If there's mirrors, if they're very shiny, basically if they're very different, they look very different from one point to another. The best objects are the objects that have that are very matte, that distributes the light, that shines on them very homogeneously in every direction. So they look the same from every point of view. In nature, they don't really exist. Most objects have a pretty strong reflectivity, especially, of course, ice or rocks. The second you have something that's quite flat or a bit shiny, you lose this. So, but the best objects are the objects that reflects very homogeneously the light that comes into them. Transparent objects are, for very similar reasons, complete no-go because you can see through them. Working photogrammetry through water or things like this, it really adds a level of complexity that's well, not necessarily manageable. Sometimes I've seen some work where people manage to work through rivers, through the relatively calm flowing rivers, but still. But an object, if you're really interested in an object that is transparent, it's not going to work unless you take the step of so in this case, spray painting the object. So like adding a coverage, making it the object non-transparent. Sometimes you can have coverage that would just wash out with water, for instance, or in some objects you don't really care to maintain the object. You just, once you have measured it, you can just throw it away. So then you can have some more permanent solutions. But overall, you really want to keep an object non-reflective, and non-transparent. That's what's going to work the best. And the last thing is repetitive pattern. So here's the Eiffel Tower. As you can see in the Eiffel Tower, there's a lot of things that just look exactly the same. Every time there's two pieces of metal crossing, it looks like the next one to the right, the next one to the left, and up and down. So from this, the computer is going to be completely blind to the difference. They're all going to look exactly the same to him. The correlation scores are going to be the same. The SIOS algorithm is going to identify objects that are not the exact same one as the same one, and it's going to completely break apart. So this is a very hard object. In nature, there's also, if you go on a beach and you work with sand, there's very little things that look more like sand than another piece of sand. To a certain degree on glaciers, what looks more like a crevasse than the next crevasse, it can be the same. I don't think I ever really encountered big problems on glaciers not being able to recognize different features, but it can happen, and it can, if it happens a bit, it's okay, but if it happens a lot in the image, it can actually build up to be a real issue. So objects that are way too repetitive with too many things that are exactly looking the same, they're going to be causing problems for photogrammetry. All right, let's finally get to example of use cases. Why would you want to use close-range photogrammetry and not drone photogrammetry and not plane photogrammetry and not just grab some satellite data from the ASTA satellite or whatever higher resolution? Or why would you not want to just use the Arctic DEM, which is rather good, or any other kind of product? So why would we do close-range photogrammetry, and also what is close-range photogrammetry? What do I mean by that? So what I mean by that is very simply a survey that is done without the help of a flying platform. So satellite, plane, drone, UAV, so unmanned aerial vehicle. It's the kind of survey that's done without this kind of help. You could also call it land-based photogrammetry because actually you don't necessarily need to be very close to the object. The technique applies for anything that's you can take pictures of from the ground. So the object of interest is either something that's relatively small, so a big boulder, a small structure on the floor, a vertical cliff or something that's relatively close, or something that you can very easily photograph from the ground. So either it's a vertical thing, or maybe you have the ability to get quite some height just by foot. For instance, if you can get to the top of the ridge and take pictures of the valley below, sometimes you can actually get a good enough point of view to reconstruct the ground below the point of view of the camera. So land-based photogrammetry is probably a better way to qualify this, but close range also covers it. So the equipment you're going to have, it's going to be a camera that's handheld, so something you just have in your hand. It might be something you're going to use with a tripod, so for it to be more stable. It might be something that you're going to hang at the end of a pole. I've seen all kind of creative way of putting a camera high up. So with the pole, with I think people using fishing rods. It's all kinds of inventive way of holding the camera away from yourself to take pictures of an object without having something with wings or with engines. Or it can also just be fixed to a structure, so akin to a time-lapse camera that you've heard about yesterday. The camera is going to be attached somewhere and just take pictures over and over again, and then there's a whole infrastructure to go behind. So that's close-range photogrammetry. It's taking images of an object of interest from the ground. So why would you use this method? So sometimes you need very, very high resolution models of the object. And even the best of drones, they're never going to give you resolutions much better than 1 centimeter of ground sampling distance. even if you fly really low, and then you start getting into the problem of vibration, and it's dangerous to fly low. And so you might want to just avoid UAVs because you need something that's higher resolution. The objects might also just be in an area where it's impossible to fly anything. If you're on the ground, that's game over. If it's inside of a building or inside a cave or somewhere that's not open air, it's game over. And legal constraints can actually be very quickly a problem. There's in most countries by now, going around with a drone and flying it for science or fun or for commercial applications is more or less constrained. There's a maximum height requirement. There's some areas where it's just completely banned. Natural reserves, for instance, you're not allowed to fly close to airports. In the case of Svalbard, all around Ny-Ålesund, there's a radio silence area, so you need very specific permits to be able to fly a thing that has a controller, and so it has some radio emissions. So there's plenty of legal constraints to using a drone or, well, of course, even a plane. That's even more complicated. So sometimes you might say, okay, a drone would be good, but it's impossible to use. And then, of course, the other case where you can't use a drone or anything is when you have a time lapse. I've heard plans of getting drone time lapses, basically having a drone that automatically takes off, do a survey, come back, and somehow plugs itself and charges again, and then go again the next day. But that's a very complicated infrastructure, very costly, and I don't think I've seen it actually put into applications, but maybe it has. But most people doing time lapses, they do it with fixed cameras. So therefore, mostly long-term surveys or for very fast changing objects. So for instance, if you want to get a 3D model of a glacier that is surging, where it's moving several meters per day, you can't really just take your survey manually, because between the first picture you take and the last picture you take, the glacier might have moved significantly. So there you would need something that's an automated time lapse. From the ground, you can't get anything flying or anything, because the frequency or the speed of the object is far too high for a single camera system or a drone. So how would we set up such a photogrammetry time lapse? I'll come back to the non-time lapse options later, but the time lapse is actually, I think, the most clear applications for close range photogrammetry, especially, well, except for very high resolution things, but like for things that could be done with the drone, sometimes you would still choose land-based photogrammetry for time lapses. And so how do we set those up? As I was saying much earlier, you need at least 2 images to get anything. It's always better to have 3, especially when you're going to have 1 master cameras and 2 cameras that are going to be slaves to it. It really adds quite a bit of strength to the to the geometry and to the quality of your model. You need, I think, 3 cameras is a good start. As I wrote here, having more than 3 cameras is extremely helpful, because equipment fails. If you have 4 cameras, one of them dies, you still have 3. And that's always better to have some safety systems there. The exact kind of camera is not really a concern. I actually work even with smartphones that were just tethered and with an app taking pictures, and that works totally fine. As always, the better the camera, the more expensive it is, and the least people are able to afford them. And if you have a camera that's worth a few $1,000s, you might not want to just attach it somewhere to a rock where people can just go around and steal it. So there's also a cost to danger ratio there to be estimated. But on a technical point of view, all kind of cameras can work. If the cameras are put outside, which in our case is going to be outside in a cold place, which again in our case it's going to be cold, you're going to need to have the equipment heated so it doesn't just die of cold. The typical DSLR camera, fancy cameras, they have a mirror, so they have some things that mechanically move. And if you have mechanical movement and it's minus 40 degrees, things can just seize up, and then you don't get data because your camera was not able to actually operate properly. So the equipment needs to be heated to avoid freeze, to avoid fog or moisture to build up. Has to be balanced with potential fungus growth as well, because if it's too nice and warm, you might suddenly have things growing up on your camera, which of course is no good. So there's a bit of work to be done there. Of course, you want your equipment to be waterproof, and as we've seen quite a few times in the Norwegian mountains and in Svalbard, foxes really like to eat cables. And so if you just have sandal cables laying around, they're going to get destroyed, and you're going to lose. Your system's just going to fail. So sometimes you need to really protect your equipment against a number of factors that are not necessarily trivial. Then your cameras need to be very well attached to the most stable objects available. So the wall of a building, the bedrock, a large boulder, the walls of a cave, all kind of things are going to get the camera stable. Because if you can be sure that the cameras are stable, that's really going to make the whole processing much easier, because you can assume the position of the camera to be stable, and then the whole work is made significantly easier. Of course, the cameras are all going to be pointing in the same place. So once you've found a way to attach your cameras, you're going to try to want to get a good frame and good angles between images. So the number of cameras is going to dictate how far from each other and how differently angled they are. If you only have 3 cameras, as I was saying earlier, about 10 degrees between 2 cameras is the goal. And the more cameras you have, the smaller angles you can get. The idea of smaller angles is that your images are going to look more similar to each other, which is going to yield better data. And also, if some camera fails, then the angle between 2 cameras is not going to get too great. So in the case of 4 cameras at 7 degrees each, if one of them failed, then the angle between 2 cameras around that failed camera is going to be 14 degrees, which is not great, but it's still possibly going to work. Whereas if you had them all 10 degrees apart, then you start having 20 degrees between 2 cameras if there's one that fails, and then that just isn't going to work. Next point is that you're going to need stable power. So if it's a very short thing, it's just going to work for a few hours, the battery of cameras can be enough, but very quickly you're going to need external power. So that's going to be, if you have the luxury of having a building nearby, you can just, have an extension cable. But of course, then you're gonna, most cases, in the middle of nature and you don't have that. So having large batteries or solar panels, if you're gonna work mostly in the summer or in areas where there's access to the sky, solar panels can be really good. Usually partnered with batteries. You'll see in some of the examples I'm going to talk about in a minute. That's very large batteries can actually work for rather large period of time. And then the last thing you need is a controller to trigger all the cameras at the same time, because you want the shadows to be all the same place when you take all the images. There's a number of things that make you really want to have a single trigger time, and also you want to make sure that you have all the images every time taking the picture. If you end up with, oh yeah, so this camera has been taking pictures every hour and this one every 25 minutes, it's going to be a hell of a work to get things to fit together. So having a central controller that just sends a trigger for everything, that's quite nice. These controllers, you can also sometimes attach sensors to them to get, so temperature, humidity, all kind of additional data that you might want to correlate with the data you're taking. You might have a small LiDAR sensor attached to it. You might have a snow depth sensor. You might have all kinds of things also attached to this central controller that's going to then compound with the data you're going to get from the photogrammetry to enhance the research and enhance what you're able to say from the data, because the geometry is often interesting, but then being able to say, okay, we saw that the temperature was sharply going up, and then we have a lot of snow that went out, or whatever. All kind of things can be done. Yes, now I have 25 minutes to talk about fun stuff. Some cases. Oh, I see in the chat there was a question about reflective objects, how to deal with water surface of snow. Yeah, well, that was that's a very good question. Snow is very white and sometimes is completely free of textures, and then you're just not going to get any data out of it. That's just a fact of life. Often there's some sustrugis or some kind of blown snow textures that's going to be enough to get data, but snow is actually a very hard topic, and fresh snow is hopeless. And water is also a problem. If you have water, you're going to end up, so the water has some optical properties, and so it's going to change the way the rays are coming back. The optical rays are projecting to the images, and then that requires quite a lot of care. For instance, only having 2 images of the same point that's underwater, and then applying some kind of corrective factor on the water area. So either by distorting the images or post-processing, just adding more distance. Like typically, if you have 2 images of something that's underwater, you're going to have a factor of multiplication to the depth of the object. That's the part that's underwater. But yeah, it's all a bit. I've seen stuff, there's some novel approaches and things being done, but it's still very specific.
Thanks.
Yes.
I was also wondering, like, for the snow, will you recommend to add more reference point, like, I mean, artificial reference point would that help, or?
So that's also one thing I've seen is, like, if you can add an additional structure to what you're taking pictures of, like if you paint the snow or something, then that's going to add points where you have data. But the end game is, if you have a field of fresh snow that's just white, there's really nothing you can do. That's just going to be, it's one case that doesn't work. So if you take pictures of snow, you're going to have to wait for it to melt a bit, create structures, create areas that are more reflective than other. That's the kind of case where you might actually want to have very sharp shadows, so the sun angles to be a bit low, creating some structures from just shading. Yeah, but that's a hard case. Working with snow is very hard.
And like, for example, in Advental, and like regarding the water, would you recommend to remove the water from the model just because of the wave and things like that? I think it would be hard for the images to match, or?
I mean, if there's waves or water structures, they're going to move, they're going to be all different, and the processor usually just going to ignore them, and in your result, you're just going to have no data where there's water. And so it's not very useful to take many pictures of areas with a lot of water, and the images might actually not manage to get attached to the rest of the bundle because there's not enough points to fit together. So yeah, I mean, water is not something photogrammetry works with.
Okay.
Simply.
Great. Thanks.
Yeah, no problem. Yes. So case number 1. There we had the paper published already 6 years ago, and there's been some continuation in the survey. As you can see from my list of years, there's some data after the publication. Up in Kvadeuksletta, so this at the very tip of the peninsula where New Yellowstone is, there's some spotted circles. I'll show you what they look like in the next slide. So there we wanted to understand how they move and how they develop year after year. And so we have some very high resolution surveys done. So 2007, 2010, and then every year from 2015 to 2018. The resolution there is better than a millimeter, so like very, very high resolution. And the equipment used was some DSLR cameras and a long pole to be higher. Actually, in the first 2 years, it wasn't with a long pole, it was with a ladder. So the the people that went up there, they just carried a ladder, and then they went up to the ladder and took pictures handheld. But then after that, we had a long camera pole, so the camera attached at the end, and then a remote trigger. We used an RTK GNSS to get control points, and the control points were represented on the ground by large rods that were put in the soil and with some kind of disc at the top that we could identify. We've noticed from the data that the RTK GNSS there was just not good enough to georeference year after year. The errors were much bigger than the displacement we were measuring. So in the end, it just gives us a scale, but the absolute reference of one model to another just wasn't working. Yes, so that's the pictures from the one of the surveys. I think that's in 2015. So you can see that's me with this long pole and a camera at the top there that's wrapped in some plastic bag or something. I don't exactly remember because it was rather moist and sometimes raining. And then we had, I think it was a Bluetooth connectivity, so we could just trigger the camera from the ground. And the guy who actually took the picture of me there also had the trigger for the camera. So I was walking little by little, trying to follow this white line on the floor and taking pictures every 10 centimeters or 20 centimeters. I don't exactly remember. The second image there on the right, that's one of the pictures. So that's what it looks like. All these circles where you have a very fine grain in the middle and rather larger grain on the side. And they have quite interesting dynamic year after year, but also in the freeze-thaw cycle. They can actually move quite fast in a few days. And the GCPs there, the control points, these rods with the disc, that's what they look like. We actually had numbers on them on some of the years, but they tend to be erased by the water. So in this specific survey, we don't see the numbers, but they're supposed to be identifiable one compared to another. That's the final result. So that's the point cloud, and you see the position of the cameras. You might understand that we were trying to get straight lines parallel to each other with about 80% overlap and things like this. The reality is, when you have a drone or a plane, it's quite easy to follow a path. When you have a pole like this and you're trying to not step on the object of interest so you would not destroy it, it's quite a bit harder to follow straight lines and be very good. So it looks a bit more messy than it really should be. But the modern photogrammetry and the structure for motion is quite lenient to imperfection in this kind of things. So it worked anyways, but of course a nicer, straighter survey would be better. As you can see, there's some areas there where there's a lot of images that are basically taking data over the exact same area, and that's just extra data we don't really need. So that's quite imperfect, but that's pretty good. So that's what the elevation looks like. So that's a grayscale. So the darker are lower and the brighter is higher. That's what it looks like. And then that's the extract from the 2014 paper, where you can see again the elevation. So there the instead of using gray, we're using colors. So there's the white is still higher, and the lowest would be this kind of pale yellow. So you see that there's some very high resolution and very high contrast, and we can really see very fine details of the topography. On the right there, that's all the arrows. We might not see the arrows very well, but the areas that are more yellow than the others, they're the areas where there's more movement. And we could really see between, so that's 2007, 2010, at the time where this paper was written, that's the only data we had. We could really see the development and this kind of concentric movement of the center fine grains of the circles of each circle going further and further to the side, while the larger boulders, the larger rocks on the sides were going inwards. Yeah, so that was case number one. Case number two, survey of snow depth. So there's different ways of getting snow depth, but we're thinking, okay, maybe we can get a slightly wider area and getting a bit more of a snow distribution approach to snow depth measurement. And so that's up in Finse, that's in the mountains of Norway. But the exact same setup could, of course, be deployed in Svalbard or anywhere you want to look at snow. We actually have some work ongoing in Lebanon, looking at some snow. Yeah, so there the setup is we want a daily data, but Finse is a place where there's a lot of wind and fog and rain, and the weather is completely inconsistent. So we put the 3 cameras bolted onto rocks, and we set them up to take a picture every hour. And so for every day, we could try to look at a triplet of image that's where as close as possible to 12 o'clock, where we have the most light, but also without fog. And sometimes, yeah, at 12 o'clock there's fog, but by 2 o'clock in the afternoon or by 11 in the morning, you have a cloud-free, fog-free image. Some days you just don't have anything, and tough luck, but that's the general idea, is to be able to have at least 1 image a day, 1 set of images a day. The area of interest, it's not actually just too close to the images. If you think about it, the immediate foreground of the image is actually not going to be visible from the next camera that's going to be 10 meters away or something. So there, the immediate foreground is actually just for your eyes. The data we're interested in is closer to the ridge before the glacier. So like there you have the sky, these 2 mountains to the side, in the middle is a big glacier, and then you have a ridge about the middle in the image, and that's the snow beneath that ridge that we were interested in. So that's kind of foreground, background area there. And at that distance, we have about a 1/4 of a meter resolution in the images, which is not great, but it's absolutely sufficient to do the science we try to do. Oh, you have to ignore the green part of my slide there. That's for the next example. Oh yeah, so we had 3 cameras that were bolted onto rocks, so like large rocks that were supposedly stable. Turns out they're not really stable because the whole area is thawing, and so the rocks are actually moving a tiny bit over the ground. It's not bedrock, sadly. If you have bedrock, it's quite stable, and then you're golden, but there it's not bedrock, it's just large boulders. And then we had a controller that was plugged to all 3 cameras, and we use 18 natural points as control points. So basically, the rocks at the top of the ridge or things that poke out of the snow that we measured with GPS. And because the resolution of the area of interest is just a 1/4 of a meter, the GPS precision is far enough. Very no problem. Very good. That's the same view of the same thing. So you can see A is the place we are, B is a closer area. You can see where all the 3 cameras were, all pointing in the area of interest where we were looking at snow depth. So you can see the cameras, they're kind of close together, but they all look in the same place with a bit of an angle. And that gives us a good overlap, a good triple stereo. C there, it's where the cameras actually are. So there's a control board there you see at the back, and then this small camera. These are Sony QX1 or whatever they're called. So the cameras are very compact, and they don't seem to have an actual body. They just look like a lens because they were designed to be attached to a smartphone to add a good camera to a smartphone. So they were not designed to be standalone cameras, which makes them smaller and easier to use and easier to integrate into this kind of equipment. So we're quite happy with them. So that's what they look like, bolted into the rock, and that's the area of interest that we see. And then that's the results. So there it's snow depth. The dark red would be up to 3 meters of snow, and the yellow is 0. There you can see that the scale on the right actually goes into -1, and of course you never have -1 meters of snow. That doesn't make any sense. But there's actually quite some noise because we're quite far, and it's snow anyways. So there's there's some noise, and sometimes you actually see some values are nonsensical. But because we have a lot of data points, we can actually do some quite robust statistics and get a good idea of the snow distribution and of the way the snow melted generally. So that was a pretty successful thing. I think it was 34 days of acquisition there, so through mid-May to mid-June, with a daily image, a selected daily image. My case number 3 is cave. So here we find sorted circles again, but there we're in southern Slovenia, close to the Croatian border. Croatian border? Or Bosnian border, I'm not quite sure anymore, but southern Slovenia. And there we have circled in red 3 cameras, and they're the exact same one as in the previous examples. They're the same cameras, the same box, the same system. In blue, it's the controller for the 3 cameras. Again, it's the same camera controller as we had in Finse. And in green there, we have lights. So these are quite powerful LED lights. The idea here is it's in a cave. We want to have daily, hourly images because the process here can actually be really quickly. You can have 5-10 centimeters of thaw and melt again and freeze again. Sorry, in a single day or in just a few hours. So we need to have a daily thing, a daily hourly acquisitions. And well, sometimes it's the lights, and even in the middle of the day, this being a bit in a cave. It's not deep down a cave, but it's not on the surface, so it gets really rather dark. So to be sure we have light every time and pretty good illumination, we just added some lights. This is the middle of nowhere. It's kilometers away from any kind of civilization. So we also needed power. So you can see this big black box just below the white circle. That's a truck battery. So the kind of battery you would find in the big, 18-wheeler or whatever you want to call them. And this battery allows for the whole system to be powered for more than a month and a half up to 2 months, with getting a picture every hour, which means switching on the lights every hour. And the controller is also tethered to some thermal sensors. So like there's a data record being kept. So it's a pretty complex system. In the walls of the cave, we added 5 GCPs to be able to have a good georeference. That's me in the cave with the theodolites there, and on the right you can see one of the pictures and what the GCPs end up looking like. So this kind of red dot drilled in the rock. The measurement here allowed for a very good relative position, relative orientation, and a good positioning reference. But of course, there's no we're not registered in a global reference because we don't care. What we want to see is how the rocks move in relation to each other, and because we have access to this bedrock with the wall of the cave, we have a very stable reference, and we can compute the movement of the soil and everything in that space. There, the resolution, there's the model there. On the left, it's the whole point cloud, the position of the 3 cameras, and the blue, white, green, red, and yellow dots there, the position of the GCPs there on the wall of the cave. And to the right, it's an extracted ortho image. As you can see, there's some wide holes. That's because the cameras, they're not actually vertical. They had to be angled. And the large rocks, they create a shadow, an area that is not observed in the images. And so you end up with this kind of shadowed areas that just aren't seen in the images. But the area of interest are not really the big rocks, it's more the soft stilt or whatever, this kind of clay-like material, the very fine sand is. And so we get pretty good, rather complete data. I think this is extracted at 1 millimeter resolution. So very fine details. And so this is not published yet. This is some preliminary data, but from what I've seen, you actually see very tiny movement, and we can detect things that move less than a millimeter between two acquisitions. It's quite amazing. We hope to be able to see a lot of things from this. And the fourth case, here we actually move inside. That's the experiment we did in 2012. I think published 4 years later, because it took some time to get very interesting things out of this. So this is a box that's about 40 centimeters wide. And there we used the corner of the box, which we measured. We just drew a identifiable cross at each corner of the box to use as control points. And then we have 4 cameras that are fixed to a big metal frame. And they all also operated from the controller. And there they take a picture every second. So that's a very high frequency time lapse. And from this, we get very, very high resolution models. We're in 1/10 of a millimeter resolution, and we're able to see really a lot of things. It's because it's inside, it's plugged to the wall, so the power distribution system is much easier than normal, and it's rather short experiments. Most experiments are just a few minutes long, so it's quite easy to operate and eventually to redo if something went wrong. So it's completely artificial, the way the whole thing works. The process we're looking at is something that we operate and we start ourselves, but that's a very interesting way to look at simulations in very high precision. Here, that's some figures from the paper that we got out of this. We can see the difference in elevation that are in millimeters, in like sub-millimeters. Can really see between 2 images or between the beginning and the end very clearly what moved. On the right there, we even have the displacement both in elevation at the top, and then in the x-axis and the y-axis, and then we can measure divergence, and we can see where there's cracks happening, where things start moving away from each other, and all kind of relationship between the different types of movement and the events that happen afterwards. And then we could see different behaviors depending on some parameters of the experiment. For instance, how much, so we had this like oil that was simulating lava, so like what kind of flux we had in lava and what kind of temperature the system was running at, and really seeing very minute details. So there we get away from real life and outside observations, but this kind of process could also be set up outside to look at a very, very small process developing if that's of interest.